Hi there and welcome. I'm Andrea Rapuzzi and I'm going to present to you a deep learning solution to the problem of downscaling applied to satellite images. The solution we'll present has won the recent ESA Air Quality and Health Challenge. The challenge aimed at downscaling, that is upsampling, satellite images about air pollution, namely NO2 and PM2.5. The input for the problem is a low-res satellite image, for example with a pixel size of 10 kilometers. And the output is the predicted high-res image, for example with 1 kilometer per pixel size. The ground truth is a peculiar one. It is composed by the reading of the pollution values at ground, that means at specific geolocated ground stations. So we have low-res images in input and a set of very sparse points in high-res as a ground truth. The idea for our final solution passes through 3 stages. Initially, we plan to implement a very simple learnable resample model using transposed convolutions. The solution is very limited in the semantical level reached by the network representational state. For this reason, we enhanced the solution to provide, before the expansive path, a contractive path, actually a full CNN. This allows the model to learn a higher semantical representation of the images. Since the need is to upsample the image, of course, the expansive path shall be longer than the contractive path, thus creating a sort of asymmetric or unbalanced UNet. The final solution design, the one that we actually implemented, removes the asymmetry in the UNet by means of an initial deterministic image upsample. This is a simple nearest neighbor upsampling. If you examine the resample image, you will notice a strong pixelation, because the image is yes in high resolution, but an artificial one with no additional information. This, nevertheless, allows us to use a standard UNet for the prediction of the high-res features. One beneficial side effect of this solution is that the architecture is independent to the scaling factor. Being fully convolutional, the model is trainable on different image sizes and scaling factors. Indeed, keeping care of a batch collation, the model is actually trainable on multiple scaling factors at the same time. We implemented and tested several UNet customizations in areas such as the input channels from 1 to dozens and the CNN backbone, ResNet, VGG, EfficientNet. Of course, we customized the output of the UNet. A segmentation UNet provides a last softmax layer to perform classification at the pixel level. Removing this last layer, we provided for a sort of regression at the pixel level. So, what happens when we have such a sparse ground truth? Of course, we will finish with a sparse backpropagation, because our loss is meaningful for just a handful of points. The first baseline results present heavily visible artifacts on the predictions, as you can appreciate from this image. Why is that? Because the loss information that propagated starting from the same few points impact the model weights in a very sparse and steady fashion. We mitigated this problem in 2 ways. First, we included heavy random augmentation to the dataset, thus breaking the spatial invariances of the ground truth. Second, we added a secondary loss term to the model. This term favors high-res prediction that, when resampled to low-res with an average aggregation, are close to the original image. These 2 modifications provided smooth prediction images as a result, and eventually allowed us to rank first in the challenge. This concludes our presentation. Once again, thank you for your time. Feel free to reach me at andrea.rapuzzi@a-sign.it.